so let's see. Yesterday, what we did was we solved the propagation equation to find the flux of cosmic rays at the Earth. And then we saw that varying some of the parameters, like the spectral index with which you inject the cosmic rays, or the number density of the sources with redshift, affects the shape and the size of the flux at the Earth. And we compared it against some data points by some cosmic ray detectors. And then I showed you this picture. And what this picture is showing is a compilation of measurements of the cosmic ray spectrum across like 7 orders of magnitude in energy and many orders of magnitude in flux in the y-axis. And you see a few features there marked as the knee, the second knee, and the ankle. So that looks messy, and what I want to do is take away some of that messiness and explain to you what we believe is the origin of those knee, second knee, ankles, and what they represent about where the cosmic rays are coming from. Okay, so for that, I will use for a little while the board. Actually, let's leave it up, because then that way you can compare what I write with that. Okay, so what I want to talk about is features in the ultra high energy cosmic ray flux. By features, I mean those kinks that you see there on top of the power law. So let's simplify that picture. Roughly, what you're seeing there is a power law, but with some extra features. So instead of plotting the flux, I'm going to plot the rate, which is proportional to that, except I'm not multiplying by the power of 2.6 in the energy in the y-axis. So this is rate of the cosmic rays that reach the Earth. And by that I mean how many reach us per square meter per day. Okay, and this is going to be a falling function of energy, of course, because we have fewer cosmic rays at high energies. So 10 to the 14 to 10 to the 20, roughly the same energy range as you see over there. So let's see, this is 15, 16, 17, 18, 19. And in the y-axis, we have 10 to the minus 8 to 100. Yeah, so minus 6, minus 4, minus 2, 0. Okay, I did it wrong, sorry. Minus 6, minus 4, minus 2, 0. This should be 4, so let me make it a bit bigger. 6, minus 4, minus 2, 0. Okay, let's leave it at that. Minus 6, minus 4, minus 2, 1. Okay, there we go. Okay, so what you're seeing there, even though it looks messy, we believe we have an explanation for where these features are coming from. And that will become apparent in a minute when I draw components that make up that flux. I'm just going to draw the 2 energy scales that we're going to be using. So PeV, remember these are mostly of galactic origin, we believe. And these are extragalactic because they cannot be contained inside the Milky Way due to the magnetic fields not being intense enough. Okay, so let's start with a low energy bit. We think that it will look something like this. Remember, these are the protons that have been accelerated by things like supernova remnants. So we run out of steam at about a few hundred TeV or 1 PeV or so, and that's where the otherwise power law starts being exponentially damped. Remember, that comes from the first order Fermi acceleration that we talked about before. But this is for protons. So I'm going to draw here protons. And iron can be accelerated to energies 26 times higher because the atomic number is 26 times higher than protons. So that means that we have essentially a similar situation here, but we can go up to higher energies. Again, it's exponentially damped because of the arguments we talked about when talking about the acceleration. And finally, remember, we don't have any more sources to accelerate particles beyond roughly these energies. And already at these energies, the flux has been, or the rate has been suppressed quite significantly. So at some point, and I'm going to talk about it in a moment, we believe there's an extragalactic component, which is the one we talked about yesterday. And that is the one that dominates at energies about 10 to the 18 electron volts and beyond. So those are the ones we were talking about yesterday when we were solving the propagation equation. So what we see in the end is, of course, not every component individually. We just measure the number of cosmic rays at different energies. And what we see is just the envelope of this thing. And the result of the different transitions that we see here is what appears in that total all-particle spectrum when we add up all the protons and all the nuclei as the knee, the second knee, and the ankle. So the protons have a maximum energy that reaches roughly about 3 PeV, and that is what we call the knee. So there should be a kink here when the exponential dampening of the flux kicks in. Remember, just as a reminder, the flux looks kind of like this. I'm going to call P. And this Emax of the protons is 3 PeV coming from Fermi acceleration. Something similar happens for iron, but as I said, the energies are higher, so the knee of the iron is also happening at higher energies, and that is roughly here. And that is like at roughly 80 PeV, which is just 3 PeV times 26, which is the atomic number of iron. So the first two features are due to the galactic cosmic ray sources essentially reaching the limit of the energies that they can go up to. So these couple of components here, these are galactic cosmic rays. And anything, as I said, that becomes beyond that needs to be extragalactic. So there is a couple of features here. It's not too clear here, but there's a kind of like a dip, and that dip here we call it the ankle. And the ankle, it's more clear in that picture. It signals the two things. First, the fact that energy losses due to pair production are significant. We talked about this yesterday. But also the fact that there's the transition between the galactic and the extragalactic components. So this is where they are meeting and where they have more or less the same size. And so there's a dip, and then it grows a little bit again. It hardens the spectrum after the ankle. And then at the very, very high energies, we have the exponential suppression due to the GCK cutoff. So this is at roughly 5 times 10 to the 19 electron volts. Okay. So just to get our bearings, again in terms of energy, remember LHC energies are around here at 10 to the 13. The energy of a light bulb turned on, 100-watt light bulb turned on during 1 second is here. So it doesn't sound like a lot, but for one proton, it is. Okay, so let's see. Let's ask and answer a few questions. Can we resolve these components, the galactic component, even the proton versus iron, and that versus the extragalactic ones? Not easily. Not just looking at the energy spectrum, we need to look at other information. And that other information is the mass composition measurements of the cosmic ray spectrum. So what I'm doing here is just plotting the result of adding all of the nuclei that are in the cosmic ray flux, protons, nitrogens, heliums, everything all the way to iron. And I'm not really distinguishing between them. I just drew the components here to illustrate what the features where the features are coming from. But in reality, we don't do this. Not in this picture. But however, we do have the capacity to distinguish with pretty large statistical uncertainty between what the signal detector would be like due to a proton and the signal would be like due to an iron. And so we have that capacity to at least partially distinguish what the flux of each one of the species is like. And that gives us some insight into the size of these components and where the transition between galactic to extragalactic could happen. And I'm going to talk more about this. So the second thing that we can use is the anisotropy or the isotropy of the incoming directions of the cosmic rays, which I have said nothing about yet. But it's important because as I said at the very beginning, cosmic rays are deflected because they travel through the extragalactic and galactic magnetic field, so they do not point back individually at their sources. But as a collection, if you wait long enough, and if there is a source in a particular direction in the sky, you should see at some level of data collection, some accumulation of cosmic rays coming from the direction of that source. So we're not quite there yet, but also we're not too far. And that means that we can already use that information to distinguish between things that come from inside the galaxy and things that come from outside the galaxy. And the reason is, inside the galaxy we can actually try to pinpoint sources, or at least say most of the sources are near the galactic center or along the galactic plane. Okay, so there's a few questions then that we cannot answer. But we want to answer, and partially I will talk about this in the next few minutes. One of them is, what are the sources of the galactic cosmic rays? We talked about supernova remnants. Those are the most likely sources. There's really no other good competitor beyond that. Where does this transition between the galactic to the extragalactic cosmic rays happens? Somewhere between 10 to the 17 and 10 to the 18 electron volts, and we don't know exactly where. And that is important because on the one hand, it will inform us how energetic those galactic sources can be, and on the other hand, it will inform us how big the flux of extragalactic cosmic rays is, which points to their identity indirectly. I said something about the mass composition measurements of the flux. Will that tell us about the nature of the sources at different energies? Yes, partially, and I will show how we do it. And finally, we don't know what the sources of the extragalactic cosmic rays are. But even if we don't, there are important things that we can claim on very generic grounds. So we can make progress even though we are pretty ignorant about their identity. Okay, so this is the basic picture of what the features in the cosmic ray flux are. Knee, second knee, and ankle. But that has been the working picture for few decades at this point. But today we're at a point where we have accumulated so much data that we can do better. And the biggest detector, which I'll say more about in a few slides, is the Pierre Auger Observatory in Argentina. It's a big collection of water tanks that catch the particles initiated by cosmic rays interacting in the air. And because it's been running for, I don't know, more than 20, maybe 25 years, I don't have the exact number, maybe 20 years, don't quote me on that. Then it can actually measure more than just a knee, a second knee, and an ankle. And what I want you to focus on is on the bottom panel here. And each one of these numbers signals a feature in the otherwise featureless power law. So it starts like a power law, then it kinks, and then it kinks again, and then it kinks again, and we have the flux suppression to the GCK cutoffs, supposedly. And that is the level of statistics that we have today. So we are resolving more and more the different features in the spectrum, which tells us more about where this knee and second knee could be. But as you can see at the very high energies, so over here, we have maybe 15 or so, 15 or so events detected even after 20 or so years, and even just upper limits in some cases, not really detections. So that's where we are today. So what else can we do with what we have just from the energy spectrum without invoking mass composition measurements or anisotropy? We can actually do a lot, and I'm going to show you one important thing. For that, I'm going to turn off the screen. Okay. So let me move this out of the way. Thank you. Very well. So we have a measurement of the energy spectrum of the cosmic rays. And with that, we can calculate the ultra high energy cosmic ray luminosity density. And I'll explain what that means in a moment and what we can do with it. And this is the luminosity density for cosmic rays above, what did I write here? 5 times 10 to the 18 electron volts. It's not a hard number. So what that means is the following. The luminosity density is this quantity. And you'll see what the units are in a moment. It is defined as the cosmic ray energy density. So how much energy is in the flux of cosmic rays that we observe, that we measure. So this is a measured quantity. And essentially what that means is you take the flux of cosmic rays that you detect and you integrate it in energy. And then that is divided by the typical cosmic ray energy loss time. And that's something we estimated yesterday on pretty generic, but I would say also solid arguments. And when you do this calculation, then it turns out that the number you get is, it's a well-known number. You might see it if you work on this field. ergs per cubic megaparsec per year. Okay, so this is the energy injected by cosmic ray sources in the local universe per unit volume per year. And I said in the local universe because remember, these cosmic rays don't travel further than about 30 megaparsecs, say 100 megaparsecs at most. So everything we're measuring comes from the local universe. And that we can use to make indirect guesses as to what the nature of the cosmic ray sources could be. Okay, I'll leave the number up there. So remember the Hellas plot that we drew a couple of days ago? That was a way to catalog potential sources of cosmic rays as a function of their size on the x-axis and the magnetic field intensity in the y-axis. And that criterion was speaking to the possibility of them being able to accelerate a particle up to a certain energy. That was one way to map out the space of potential sources. This is a different way, but now it's based on that quantity. So now we're going to write the energy, the luminosity density, as this quantity. So we're going to assume that there is some population of cosmic ray sources with a number density, an effective number density, and an effective luminosity. And what does that mean? I'm assuming that all of the sources inside the population are identical, and any one of them is prototypical of any member of the population. The number density of the sources is this, so how many sources per cubic megaparsec, and each one of these sources is emitting some luminosity in cosmic rays, so ergs per year. And I'm going to plot what that condition implies for this product. So if I write here actually I can write just an effective. Let me actually write it here so you have it. This is the effective source number density. All right, so this is the effective, this is cosmic ray source, I should say. Cosmic ray luminosity per source. This is for one source. So you multiply these two numbers, you get the total from the whole population. This is an effective in cubic megaparsecs, and this is going to be L effective in, again, as I said in the beginning, astrophysicists like to mix CGS and SI units, so it's in ergs per second. And 1 erg is, I always have to look it up, 10 to the minus 7 joules. Okay. Let me write a few orders of magnitude here, 10 to the minus 10. This is 10 squared. So let's see, 8 minus 6 minus 4 minus 2, 0. Okay. Okay, and this goes from 10 to the 34 in those units to 10 to the 48. So this is 36, 38, 40, 42, 44, 46. Okay, not so bad. 44 and 46. Okay, so there's one extra condition. Actually, before that, let me write where you can look at this plot in more detail. Certainly better drawn than I'm doing it here. This is in a review we wrote some years ago, Alves Batista and others. This is in the Frontiers Astronomy. Space. And this is in 2019. Okay, so there's one extra piece of information here that I haven't mentioned, and that is a detector like the Auger observatory that I mentioned a bit ago, which I will elaborate on shortly. It can put limits on the minimum density of sources from the lack of clusters of cosmic rays coming from different parts of the sky. Let me unpack that. So, as I said a little bit ago, if one were to see a collection of cosmic rays coming from a particular direction in the sky, and it's not over a uniform sky otherwise, then one could claim that there is a source in that particular direction. That argument can be made statistically rigorously, and the Auger observatory does not see any such accumulation of events across the sky with any statistical significance. So what it can claim is that the number density of sources needs to be quite big because that means that each source is individually quite weak and there's many of them. So none of them is popping up and becoming a source in terms of giving us clusters of cosmic rays from the direction where it is at. And from that argument, then they say the number density of sources needs to be at least bigger than this number. Some number between 10 to the minus 6 and 10 to the minus 4. So if you want to know the details about how this is done, you can look at the Auger paper. This is a Jacob in 2013. I think it's been updated ever since, but the argument is the same. So if the number density were, let's see, if it's too big, then that means we don't have any one individual source that is dominant of the flux. If it's too small, we would have seen one dominant source, and we have not. So that is the argument. Very well. So then how do we use that inference that were there? Let's draw the line that corresponds to the product E cosmic ray times QR equals to 5 times 10 to the 44. When we decompose it in terms of these two, it looks like, let me see if I do it correctly, looks like this. Very well. So across this line is where that condition is met. And we can do something similar to what we did before with the Hillas plot. We can draw on top of this blobs where different candidate populations of sources could lie. So for instance, galaxy clusters, we know from astrophysical measurements, are here. Starburst galaxies, which are galaxies where the rate of star formation is 10 to 100 times higher than in the Milky Way, they're here. These are all potential sources of cosmic rays that satisfy to some degree the Hillas criterion that we talked about some time ago. Gamma ray bursts, remember these intense flashes of gamma ray emission due to especially luminous supernova are here. And then things like neutron star mergers are over here. So there is then some indication that if we want to explain what we measure for the flux of cosmic rays, some of the source populations do better than the others. This is also pretty, let's say, first pass. You can always wiggle the models and get most of these classes to actually be able to explain the cosmic ray flux. But some of them are naturally better than others at explaining it. For instance, neutron star mergers are pretty good at it. And starburst galaxies, because you have much star formation, you have many of these shocks that we were talking about a couple of days ago, and you expect those conditions to be met more easily. So just from measuring the cosmic ray spectrum and integrated in energy and knowing how long they would stay, they would take to lose a significant part of their energy like we did yesterday, we can then infer what the most likely candidates could be for their origin. And this is of course for extragalactic cosmic rays. So now we're talking about the high-end component of that spectrum that I drew over there. Okay, I'm going to talk about something a bit different now. So is there any question about this? Okay, I don't see anything. Good. I don't know if that's good or not. I'll choose to believe it's good. You can always ask questions. Yes.
So I understand that the graph induces the and E, but is it? And then you also talked about different kinds of nuclei. And I was wondering, like, what makes this iron peak so manifesting compared to, let's say, other nuclei, possibly having peaks as well?
That's a good question. So the question is, let me see if I translate correctly, but is that there are many needs from different mass groups, right, between protons and iron, and that is absolutely true. So in reality, what you are seeing is the result of all the needs. Yes, they are there, and typically we don't. It's difficult to make in abundance, at least, elements heavier than iron, so we stop counting the knees after iron. But you're absolutely right, there's many knees, we just don't have the resolution to look at them. So we look at the ones that are further apart, where there's a better chance of just telling them apart. Yeah, but they should be there, yeah. Yeah. In fact, and you should also have, if you think about it a bit more, there's a GCK cutoff for every species here as well. So, yeah, this is a simplified picture. Okay, so let me talk about any other question. Okay, good. Let me talk about something I've been mentioning in passing, and then after that, I think I will switch to talking about neutrinos, because now we have all the tools to do it. And that is cosmic ray magnetic deflections. So I've been saying repeatedly that one of the reasons we cannot find the sources of ultra-high energy cosmic rays, which are supposedly extragalactic cosmic accelerators, is because the cosmic rays are bent as they travel to us, and then we cannot use them to pinpoint back at their sources. There's magnetic fields in extragalactic space and in the Milky Way itself. And let's start with the extragalactic ones, which are the least known. So the extragalactic magnetic fields, we think, should be of order nanogauss. And we have not measured it, and we don't know exactly what their origin should be. Proposals are that these are just primordial magnetic fields that were growing together with just the growth of a large-scale structure. If you want to know more about this, my go-to reference is typically this one, Siegel, Mignati, and Enslin. And this is a 2004 PRD. They do some Monte Carlo simulations of cosmic propagation with magnetic fields. So let's calculate let's just write what the average, by that average I mean the root mean square deviation of the deflections in the cosmic rays are due to the extragalactic magnetic field. And that is roughly 0.8 degrees times the charge. Let me write it first and then we'll talk about it. This is 1/2. Okay, and you can more or less easily understand what's going on here. So this is deceptively small. So you can say, okay, if a particle or a cosmic ray is propagating over 10 megaparsecs, you're going to get 0.8 deflection, which doesn't sound like a lot. There's two arguments against that. One is that in 1 degree in the sky, there's literally hundreds of millions of sources. So just being able to resolve a direction with 1 degree in the sky doesn't really pinpoint to one particular source. That's one thing. And the second thing is why this small number is deceptive is because if you plug in numbers that are slightly worse than our baseline numbers, then this 0.8 quickly becomes bigger than that. So let's first understand what's going on. And higher charges bend more. Of course, there's more protons, so you bend more strongly. If you have a high E, you have a higher rigidity, so it's more difficult to bend your trajectory. The longer you travel, the more you bend. And if you have a magnetic field that is higher than the nanogauss, of course, you will bend also more. That's roughly the understanding of what's going on there. So 0.8 sounds like a small number, but when you simulate this, which I cannot do on the board, but I can draw the results of, you find a distribution of deflection angles. So now it's not just the root mean square, but it's actually from a sample of cosmic rays that you're throwing from a population of sources, you can measure what the distribution is of the deflection angle between their original straight line direction and the direction that they end up having once they reach the Earth. And measure this in the following way. So this is 0, this is 180. Let's say 50, 100, 150. Right. And this is a distribution, so a cumulative distribution. Okay, this is 1, this is 0. It's a cumulative distribution, this is normalized. So this is 0.8, this is 0.4. I'm just going to mark a couple of numbers that are important here. And it looks kind of like this. So yeah, it peaks at 0, so close to the 0.8 that we were talking about. That means that the most likely value, if you were to sample any cosmic ray from that simulation, will be something that is close to a cosmic ray that has a deflection close to a value of 0. But if you were to sample many, then you will end up in some cases with deflections that are up to tens of degrees or so. And that then means that your chances, even this is, by the way, this is just for a proton. So proton of, I didn't write it down. Proton of 10 to the 20 electron volts probably. For a iron or just anything that is more charged than a proton, then these deviations are even stronger. So what I was saying is that in reality, even for a proton, then you have a sizable chance that that proton no longer points at its original direction just from the extragalactic propagation. And then on top of that, there's the fact that the Milky Way itself has a magnetic field. And that introduces a second source of magnetic deflections, which worsens the problem. So the magnetic field, the galactic magnetic field, by galactic I mean Milky Way. So galactic with a capital G typically means our own galaxy. This is for the micro-Gauss. And remember, I think I said at the beginning, the geomagnetic field, or magnetic field of the Earth is between 0.25 and 0.68 Gauss. So these are truly small quantities, but still they're important. So do you know how the magnetic fields are measured, by the way, in space, at least for the Milky Way? Okay. Does anybody know about Faraday rotation? Okay. So the way it works, let me see if I have a picture here. Yeah, okay, I don't, but I'll explain. So the way it works is when a photon goes through plasma, it will have its polarization changed depending on the size of the magnetic field that the plasma contains. And that rotation in the polarization of the light, of the wave that is going through the plasma is equal to the rotation measure, I'll say what it is in a moment, and the wavelength squared of the wave that is going through it. And the rotation measure is a measure of how much column depth of electrons the wave encounters as it's going through the plasma. So this is, actually let me not do it from memory. Yeah. And I'm going to skip all the prefactors. So you're going from the 0 to the size of the region you're crossing. This is the number density of electrons, L. This is in cubic centimeters. The magnetic field in that direction that you're crossing the region through. I'm going to write in nanogauss, but remember, the magnetic field actually is microgauss. And then this is the size of the path length that you're crossing through the plasma. So what astronomers do is by measuring the amount of matter across different directions in the sky, they can infer what the density of electrons is across different directions inside the Milky Way. So this is a measured quantity. So the electron number density this is measured. There are tracers to measure that. And this is what we want to find out. So we want to map the magnetic field intensity across different path lengths along the Milky Way structure. And what they also measure, by the way, is the polarization of the waves that they detect. So this is the change in polarization. This over here. And this is what I was telling you, it's called a rotation measure. So from measuring this independently from this, then they're able to find the magnetic field in different parts of the Milky Way. And if we have that, then we can estimate what the deflections are of any cosmic ray crossing the magnetic field of the Milky Way. And the structure of that expression is similar to what I wrote there, but the quantities are slightly different. So the deflection here is going to be roughly 16 degrees. So just the magnitude is a lot bigger, times the charge, times, let me normalize it to slightly different numbers than before. This is the dependence on the quantities is the same, it's just the magnitudes that are different. And this is what matters for us. L is typically order 3 kiloparsecs. Remember this, the distances in the Milky Way are measured in kiloparsecs. The diameter of the Milky Way is 30 kiloparsecs. And this is the size of this. So from combining this, not this, sorry, this and this, we're measuring B, and B now goes in here, and then we can calculate the deflection of a cosmic ray with a certain energy that goes through the Milky Way, traversing a path that takes it through a distance L in some direction inside the galaxy. Okay, and the first thing you should notice is this. 16 degrees for protons, so if I fix it to 1, is a lot bigger than 0.8. So the size of the magnetic field in the Milky Way is what's doing that. And that means that even if we're lucky and we get an extragalactic proton that is reaching the Milky Way without having endured much deflection on the extragalactic magnetic field, it will most certainly suffer a big deflection once it reaches the magnetic field of the Milky Way. You want to know more about this? You want to know about how to build these magnetic fields? This is a whole industry of people doing that. Actually, that's not true. It's like two groups, and they produce papers like it was an industry. So, Janssen and Farrar. And there's many models, but if you want to look at one of the early ones, is from a few years ago. And then if you want to know more about how to derive this in more detail, you can also look at one of the Auger papers from some years ago. This is astroparticle physics, 2007. Yeah, 2007. Okay, so then the question is, actually before asking a question, I want to show you how that looks when it's done properly with data. And then I'll ask a question, and then we will pause. Okay. No, this is cosmological neutrinos, so I want to jump. Sorry about that. I'm going to spoil some of the things because I reordered it. So this is what I meant by Faraday rotation. So the astronomers will measure the amount of polarization change across the sky, which is what you see here in the sky map on the left, in radians per square meter, which is the units they use to measure polarization change, or rotation measure rather. And then from the equation that I wrote on the board, which is the one that is down there, so this one, then they can infer the magnetic field intensity across different parts of the Milky Way structure. And it's all in micro-Gauss scale, but you see the little arrows that are pointing to not just the intensity, but we can also infer the orientation of the field lines. And that means we can unlike the extragalactic magnetic field, on which we only have some intensity guesstimated for the Milky Way, we actually have structured magnetic fields. Okay, so when we do that, then you can go back with that knowledge of the magnetic field, and now you want to calculate what the deflections of the cosmic rays are. This is for 60 EeV protons, so 60 times 10 to the 18 protons, electron volts protons, and that's how it looks in terms of deflections across the sky due to the Milky Way's magnetic field. You see that close to the center of that sky map, so close to where most of the stuff in the Milky Way is, that's where you get structure that can subtend high magnetic fields, and that's where you expect the deflections to be bigger, and that's why it's redder than in the outskirts where you have less stuff that can hold magnetic fields. So one extreme example of this happened not very long ago. So you might have heard about this particle called the Amaterasu particle. And let me give you a bit of backstory. About 20 years ago, or maybe 25 at this point, there was a particle called the Oh My God particle. And it was because, oh my God, it had very, very high energies. And the energies of that was, I think, 320 EeV. Back in the day, I think it was either the AGASA or the high-res detectors, the detector that detected it. It's no longer operational. And that is still to this day the highest energy cosmic ray we've seen so far. This is the second highest one, and it was reported last year, not by the Pierre observatory that I was talking about, but by the telescope array cosmic ray detector, which uses fluorescence detectors to see cosmic rays. I'll talk about this in a moment. Now, this is a 244 EeV proton, or nucleus, that we don't know the identity of. Actually, we don't know if it was a proton or an iron or whatever, something in between. The only thing we know is that it came from a region of the sky, the one that is encircled by the dashed lines, where there is little matter in terms of potential accelerators of ultra-high energy cosmic rays. There's nothing there that is looking intense, nothing that is producing gamma rays that could be a signal of that being a cosmic ray accelerator as well. So people were wondering why then we have one of the highest particles we've seen coming from a region of the sky where there seems to be nothing that could produce it. And then they were invoking things like beyond standard model explanations, like maybe there is some Lorentz invariance violation that makes the particle live longer than it should, and then it's not really coming from the direction of the void, but it's coming from somewhere else, and it's being bent, and because it's living longer, it's being because of the Lorentz invariance violation, it's living longer, and therefore it can be bent longer. And in reality, it could be coming from somewhere else in the sky, and then the direction that we detected it at is just the result of that longer bending. Okay, none of that really is necessary. So you can always invoke BSM to explain weird things, but it only makes sense to do it if you cannot explain it without BSM. That's just a rule of life. And what these people did recently, and that's why I wanted to bring this one up, and by recently I mean like a few months ago, maybe a couple months ago, is they inferred what is the most likely direction of the source of that one particle, the Amaterasu particle, that's how it was baptized, given the large uncertainties in the magnetic field strengths inside the Milky Way and outside the Milky Way. And they needed to make some assumptions. They don't know if it was a proton or something heavier than that. That's why you see 3 different color schemes, assuming that this was a proton or something intermediate like a nitrogen or something like that, and something heavy like an iron. And then they are just undoing the effects of the bending of the cosmic ray inside the Milky Way and in extragalactic space, accounting for uncertainties in the models of the magnetic fields and uncertainties in the energies that are measured for this particle. And what they find is that when they do this, the most likely part of the sky that could hold the source of that one particle is, if it's a light particle, then it's this one and there's really nothing that is nearby. But if they now allow the particle to be not a proton but something heavier, eventually they run into regions that do contain potential cosmic ray accelerators, like these 2 or 3 sources that are labeled over here. So these are probably active galactic nuclei that could be able to make particles of energies that reach a couple hundred eV or so. And that is just something we find by undoing the effects of deflection of the cosmic rays. If we had not done that, then indeed it would look like the particle was coming from somewhere in the void, and then we would be left without that potential origin, and that's why the power that's where the power of accounting for magnetic field deflections comes from. It allows us to point in the right direction. Okay. Any questions? Yes.
What is the determining factor? What gives you the upper boundary of maximum energy you can reach with an AGN?
It's related to the arguments I went by yesterday. So it depends on a few things. First, the magnetic field that the AGN can subtend. Second, the compactness of the source, so how much energy you can dump in a very small space that could allow us to impart that into the cosmic ray. And third, the Lorentz factor of the relativistic outflow where the particle is accelerated. And for an AGN, that is about 100 or 300 in terms of gamma. So those are rough numbers, but that is what's limiting the maximum energy you can reach with an AGN. Yeah. Any other question? Okay. How about we pause for a few minutes and then we come back to neutrinos. Let's now edge a little bit closer to the stuff I actually work on my daily life. And that is neutrinos. So we talked about protons interacting with the CMB and the extragalactic background light yesterday, and how that induces this GCK cutoff at the highest energies. But that's not the only thing those inelastic interactions induce. They also produce neutrinos. And those are the neutrinos we're going to talk about now. They are called cosmogenic neutrinos. And that's just because these are born in the cosmos, again. Rather during the propagation of the ultra-high energy cosmic rays instead of inside an astrophysical source. And we'll talk about those probably tomorrow, the ones that are born inside sources. These are just the ones that are born when the ultra-high energy cosmic rays are interacting with the CMB and the EBL photons. Okay, so remember when that happens, there is let me write it again. So there's a delta resonance being produced. I don't remember if I mentioned it yesterday, but this is essentially an excited proton. Yeah, has a higher mass. There's a different configuration of quarks, but it's still UUD. It quickly decays, and then when it decays, it gives us at least 1/3 of the time. It gives us a neutron plus a charged pion. and the charged pion decays into a mu plus a nu mu, and the muon decays further into neutrinos and positrons. So we get out of this 2 mu neutrinos, 1 electroneutrino. You'll notice that I'm not distinguishing, and I won't distinguish typically between nu and nu bars, because in practice the detectors that we have to see those neutrinos at those energies cannot distinguish between nu and nu bar. This is not true for low energy detectors where we actually do have the capacity. So let's talk a bit of history. So the CMB was discovered in 1965 by Penzias and Wilson, as I said a couple days ago. So CMB discovered, and then the GCK cutoff of the cosmic rays, which is related to this interaction, that was in 1966 by Greisen, Zatsepin, and Kuzmin. But then it took only 3 more years for people to realize that you should be getting neutrinos also. So in 1969, cosmogenic neutrinos were proposed, and the people that thought about this for the first time were Berezinski and Zatsepin, the same Zatsepin as here. So in a paper, in this paper, Berezinski and Zatsepin. And this is a PLB, a physics letters B, in 1969. So, spoiler alert, those neutrinos that were predicted more than 50 years ago have not been seen yet. So, just to clarify, the neutrinos that I'm going to be talking about, these cosmogenic neutrinos, the ones that are born as the protons propagate and interact with the cosmological photon backgrounds, they haven't been seen yet. But we have seen high energy neutrinos of astrophysical origin. Those are the ones that the IceCube Neutrino Telescope, which you might have heard about, detected. So I'll come to those tomorrow. For today, let's talk about these first, because they're the OG astrophysical high energy neutrinos. So why are they interesting? There's 2 reasons. The first one is, as we will see in a moment, these neutrinos have energies of the order of eeV. So this is 10 to the 18 electron volts in our usual units. And that means that you get to probe, and by the way, this is not just eeV. I should actually say eeV to 100 eV or more. So that means that we're probing the high end of the cosmic ray spectrum, the ones that no longer reach us because they're being cut off by the GCK dampening. So whereas the cosmic rays for energies that are above 5 times 10 to the 19 won't reach us because of these interactions, the secondary neutrinos that the protons make will reach us, because once you make a neutrino, it's difficult to kill. So they will get to us. And the second reason why they are interesting is because for the same reason, then the neutrinos reach us from distances that are farther away than the distances that the cosmic rays can reach us from. So again, the GCK cutoff is imposing a distance horizon for the cosmic rays of about 30 megaparsecs. So anything above 5 times 10 to the 19 needs to come from the local universe. That is true for cosmic rays. It is not true for neutrinos. So these interactions still happen at distances beyond 30 megaparsecs. The protons don't reach us, but the neutrinos do. So on the one hand, cosmogenic neutrinos are directly probing the acceleration of cosmic rays to energies beyond the GCK cutoff. On the other hand, they are probing distances to the sources that are farther away than the GCK cosmic ray horizon. That's why it's interesting to look at them. We can indirectly learn about the cosmic rays just from looking at the neutrinos that they make. Okay. By the way, there's something I should mention here. I keep writing only pi pluses. There are other processes that will give you pi minuses. So the processes there are charge conjugated processes that will also give you the flip version of those. And I'm not writing it here because I'm only writing this dominant means of production, which is via this particular resonance. There's extra production channels that will give you also pi minuses. Okay, so let's talk, just to let what I said sink in, let's talk energetics. Energetics. Okay, so I think back maybe a couple of days ago, or maybe yesterday, I wrote down what the condition is between the proton energy and the photon energy to hit this resonance. So that delta resonance has a mass of 1.232 GeV. That's what the 1232 means. And that imposes a condition for the creation of that particle on the proton and the photon energy of about 0.16 GeV squared. So there we go. And the second piece of the argument is that if we have an energy for the proton of EP, then the energy on average of the outgoing pion is 20% of that. And this is something that it's not something I can show you here. It's something that comes out of particle shower simulations. And the reason is you need to know how to hadronize things, right? So you're letting this decay, and then you are having a distribution of final state particles. On average, each pion takes 20%. In reality, there's a distribution of what the fraction of energy that the pion receives is. So for now, let's just take what the average number is. If you want to look at the details of how this is done, the go-to reference is Kellner and Aharonian. In 2008. Okay, so this comes from simulations, really. And then in a single pion decay, so just one of those processes, each one of the final state particles, so there's 4 of them, 1, 2, 3, 4, takes on average 1/4 of the parent pion energy. So each one of the neutrinos takes 1/4. Again, this is on average. Okay, so that means that the energy of one of the neutrinos that comes out of that network of processes is on average 5% of the parent proton energy. So now we have 2 conditions. One on the proton and photon energies, and 2 is a relation between the neutrino energy and the parent proton energy, and we can use both. But before that, let's look at this. So as I said a little bit ago, we have not seen cosmogenic neutrinos, but we have seen neutrinos of lower energy but of astrophysical origin. So if we see a neutrino of 1 PeV, which we have, IceCube has, this is 10 to the 15 electron volts. This is as high, roughly as high a neutrino as we have seen so far. Then that implies that most likely that was made by a parent proton of an energy of 20 or so PeV, which we know exists. I mean, we measure the cosmic ray flux, and we know that there's plenty of these lying around. If instead we were to see one neutrino of 10 eV, which we have not. So this is 10 to the 19 electron volts. Then that would imply a parent proton energy of 200 eeV. So that's 2 times 10 to the 20 electron volts, beyond the GCK cutoff of 5 times 10 to the 19 electron volts, sizably beyond. So we see this. These ones we do see at the Earth. These protons, I mean. These ones, we don't. And the only way then to see, quote unquote, see them is via the secondarity they produce, the neutrinos, which we could in principle see if we had a big enough detector. More about that tomorrow. Okay, so as I was saying, we have two conditions, 1, 2, and we can put them together to find a relation between the neutrino energy that gets produced and the energy of the photon spectrum with which the protons are interacting. And this will become useful in a moment. So this relation is 0.01 GeV divided by the photon spectrum in GeV. Okay, so let's use this. Is that clear, by the way? Okay, I don't see many intrigued faces yet. Okay, so let's go back to what we were talking about yesterday. We talked about the CMB and the extragalactic background light as the photon backgrounds for the protons to interact on. Let me redraw it roughly again here. So we had the photon energy. I'm going to write it in log scale, like yesterday. Log 10 of the photon energy in GeV. So the same units that we're using here. And this goes from very small energies to okay energies. 16, 14, 12, 10, 8. And on the y-axis we had the photon number density. And this is the picture I'm drawing now is in the local universe. Now, these numbers are larger if we move to higher redshifts. So this is 10 to the minus 6. This is 1,000. Let's see. Minus 4, minus 3, minus 2, minus 1, 0, 1, 2. Okay. I'm just going to write a few. 10 to the minus 1, 10 to the minus 3, 10 to the minus 1. Okay, 1 and 2. Okay, and the CMB looks, is a black body spectrum, so it looks kind of like this, very roughly. And the peak is at 0.23 millielectron volts, like we said yesterday. The EBL has a more complicated shape because you remember it has two bumps. One is from the UV and optical emission of the stars. One is from the absorption of that by dust and the re-emission at lower energies. So original and then re-emitted. EBL, CMB. Why am I drawing this? Because it will become important in a moment. This is roughly at -9, the peak in GeV. This is roughly at minus, oops, well, it should be a bit more to the left, I'm sorry. This should be -11, apologies for that. Okay, so now we have a spectrum. Let's forget about the width of the spectra, of the photon spectra. Let's just talk about the peak positions. And let's use the relation we have to find out what the energies of the neutrinos that those interactions produce should be. And if we think about the CMB first, then the neutrino energies are roughly, again, 0.01 GeV divided by 10 to the minus 12. So this is about 0.1 millielectron volts. And that is 10 to the 10, actually this is exact, 10 to the 10 GeV, 10 to the 19 eV. So the neutrinos we expect from protons interacting with the CMB have energies that are already very near even the GCK cutoff. If we now do it for the EBL, we're going to have two peaks, so we need to do this calculation twice. Let's do it first for the high energy, actually for the low energy peak. And those will give us, I'm going to write it in full, 0.01 GeV divided by 10 to the minus 11. So this low energy peak. That gives us 10 to the 9 GeV neutrinos. And if we do it for the high energy peak, then same calculation, different photon peak, that is 10 to the 7 GeV. Okay, so now we're talking about energies between 10 to the 7 GeV and 10 to the 10 GeV at most. And if we include the width of the photon spectrum, which we have neglected for the calculation, you can even reach higher energies than that. So the ballpark of the cosmogenic neutrinos is around this, cosmogenic neutrino energies. Okay, so that's just for us to get our bearings, right? But then we need to actually calculate a flux of neutrinos at the Earth. And this is done in a similar fashion as we did for the cosmic rays. I will not go into as much detail as I did for the cosmic rays, but I think it's important to show that now, instead of having one type of particle being propagated, we have two, and they are related to each other. Now, the neutrinos come from the protons, so we need to evolve protons and neutrinos at the same time. So let me just write the propagation equation. For the cosmic rays is the one that I wrote yesterday. So this is just the change in density, and we had all the energy loss and gain terms that I had written before. Let me just repeat them here. So the adiabatic energy losses, the losses by pair production, the losses that are due to the inelastic proton-photon interactions, the one that will give us the neutrinos. Okay. And finally, just the injection of the cosmic rays by the sources along the way. I'm missing a P here. Okay, yes, so that's just the same equation I wrote yesterday. But now we have a second one, and that is simpler than that one, because, as I said, neutrinos, once they're made, they just essentially free stream. So the equation looks the same at the beginning. Oh, sorry, there's a minus here. Yeah. They do need to, there is also a redshift change in their energy to the cosmological expansion, so we need the first term, definitely. So that's the same as for cosmic rays. And then the only other term that comes in is the injection of neutrinos that come, in this case, not from a collection of sources, but rather from these interactions. So remember, each time one proton is interacting with a photon, after the whole decay process, we're getting 3 neutrinos plus stuff. So these neutrinos now need to be injected at each redshift into the transport equation of the neutrinos. There's no other energy loss terms. Well, is there no energy loss terms really for neutrinos? Think about what process could be dampening the flux of neutrinos of very, very high energies. So there's an idea, it's called the Z-burst idea, and that happens when we now think not only about the cosmological photon backgrounds, but about the Rayleigh neutrino background. And in that case, this is not part of the equation, I'm just saying it as a side note. You would have neutrino interactions. One is high energy, so one is the one that is coming from that process. So actually, let me write it as cosmogenic. And the other one is the Rayleigh neutrino background neutrino. If you hit the right energy, you're going to get a Z on shell. And then that Z can decay and give you, well, typically hadronicity, and that'll give you stuff. So in principle, there is also a horizon beyond which neutrinos will not reach us because they will be killed off by producing Z's on shell. And of course, the Z's will then decay, and part of the decay includes neutrinos, but those are lower energy neutrinos than the original cosmogenic one. Do you know what the energy should be to hit that on-shell Z production? What the energy of the neutrino should be? Yeah, it's like 10 to the 25 electron volts. There's no source of neutrinos, not cosmogenic, not astrophysical, that can make neutrinos of those energies. The only sources that could make neutrinos up to 10 to the 25 electron volts are all exotic, and exotic here is a bit subjective. So you could have topological defects or cosmological strings that will emit particles, including neutrinos, that reach up to very, very high energies. But that's about it. So the Z-burst idea is an interesting one, but we just don't happen to have neutrinos that will trigger this on-shell production of Z. At least we don't think we do. Okay, so just to round out the problem here, let's finish with showing you how the flux of neutrinos, cosmogenic neutrinos, looks once they reach the Earth. And as before, I will not do the solution on the board. This is the result of a numerical solution where we propagate those equations numerically and together. And I'll show you how that result looks. So now this is neutrino energy in the x-axis, and again, I'm going to use log scale. This would go from very low energies, where we don't expect cosmological neutrinos to be at, to the energies where we expect them to be. So 5, 6, 7, 8, 9, 10. Okay, this is horrible. 5. I'm really bad at drawing tick marks. Let me do it properly, otherwise it won't make sense. Okay. 5, 6, 7, 8, 9, 10, 11. Okay. This is nowhere near uniform, but you know, as close as I can make it. 11. And this is going to be the neutrino flux at the Earth. And I'm going to write it here, all flavor. And by that I mean I'm counting the neutrinos, the new E's, the new mu's, and I am allowing them to oscillate on their way from the sources to the Earth. I'll talk more about neutrino mixing tomorrow. I think it's building up on what Joachim said a couple weeks ago. So this is a quantity like this, E nu squared times J nu. So this is the energy flux, really. So it's in units of GeV per centimeter square per second per steradian. This is a diffuse flux, so it's a diffuse anisotropic, so we don't have sources. This is just the protons being making the neutrinos as they propagate. And as before, this quantity J nu is the density of neutrinos once they reach the Earth, so Z of 0, multiplied by the factor of C over 4 pi to give it the right units. So this will be from 10 to the minus, what is this, 12 to 10 to the minus 6. Let's try this, 11, 12. Am I right? Yes. 11, 10, 9, 8, 7. Okay. 10 to the minus 10, 10 to the minus 9, 10 to the minus 8, and 10 to the minus 7. So there are observations of cosmic rays at high energies. As I said, IceCube has seen neutrinos, and I'll show more about this tomorrow. But the observations that they have end at about 10 PeV, roughly below that. It's kind of like a power law, what they see. So I'm just going to draw it here, and I will elaborate on that tomorrow. So this is IceCube. They do have searches for neutrinos of higher energies that have come empty-handed. So there's no observation of neutrino above this. And that means that the flux at higher energies needs to be below some upper limit that they placed. So it cannot be larger than that, the part that is shaded, because otherwise they would have seen something at those energies, and they have not. From solving our equation, and there are certain assumptions, like I'm going to assume here for the purpose of this plot that the maximum proton energy, like we did yesterday for the protons, is 10 to the 20.5 electron volts, and the protons are injected with a spectral index of 2.5, and the sources are evolving like the star formation rate with redshift. So there's some baseline inoffensive assumptions. The first thing we find then is what comes from the protons interacting with the CMB photons, and that will have that spectrum will have a peak at the energies that we calculated here, 10 to the 10. So over here, and it will look kind of like this. So this is interactions in the CMB. And then for interactions on the EBL, you will have a neutrino spectrum with two peaks at those two energies, 10 to the 9 GeV and 10 to the 7 GeV. So over here, and over here, and it will be, as you would expect, a double bump. Let me see if I can draw it correctly. Like this. So these are the EBL. And then I neglected earlier on purpose showing that sometimes you do get neutrons as part of the process, right? So you get P plus photons and plus P plus. And then the neutrinos I've been talking about are the neutrinos that come from the pion decay, but the neutron decays as well. It beta decays, and when it does, it's giving nu E bars. But those nu E bars are lower energy than the neutrinos that come from the pion decay. Do you know why that is the case? The mass of the neutron and the mass of the proton, they are too similar. So there's only very little energy left to give to the final state nu E bar. And that means that even though you're making cosmogenic nu E bars, those come at a lower energy. They have the same shape though, and they peak where they should peak, but they are rather at low energies. So these come from neutron decay. So overall, what we see, what we expect to see, is this spectrum. And that is the spectrum of cosmogenic neutrinos. Okay, so to close out that thought, let me just show how that looks when we move around some of the cosmic ray parameters. And in the same way that the parameters modified the cosmic ray spectrum, they will modify the associated cosmogenic neutrino flux. Okay, sorry, I had that. Oh, okay, I forgot to mention this. I apologize. Let me come back to that in a moment. Let me talk about first cosmogenic neutrinos, which are here. Yeah, so yesterday I showed the plot on the left. That is what the cosmic ray spectrum looks like at the Earth if we change the maximum proton energy. The higher the maximum energy, the more cosmic rays we expect at the highest energies, evidently. And the same thing happens for neutrinos. So as we crank up the maximum proton energy, we get more protons that can interact with photons and trigger the delta resonance and other processes that are neutrino making. And so we get more neutrinos at high energies. Similarly, if we change the spectral index of the injected cosmic rays, if they are too steep, so if they are too different from the baseline assumption of 2.5, then we are no longer able to fit the cosmic ray data points well. And if they are too steep, like minus 2.7 or something like that, then that means that at the highest energies we get fewer neutrinos, and that kills off the amount of neutrinos in the flux at the Earth. So it's a similar trend as the cosmic rays. And finally, this is related to what I was saying earlier. Unlike cosmic rays, which need to come from the local universe because of the GCK cutoff, neutrinos can come from further away. So if you look at the plot on the right, you will see that the total is the dashed line. So this is kind of like what I drew in the board. And most of it, most of it is coming from from proton-photon interactions that are between z of 0.5 and 1.5, which is a few gigaparsecs in size. So this is this little contribution over here, of that line. But even when you go further out to a redshift of between 2.5 and 4, which for cosmic rays means we would not see the cosmic rays generated at those redshifts, we do get a sizable contribution from those cosmogenic neutrinos, which is this line over here. So in the case of neutrinos, it does matter what the sources are injecting past the GCK cutoff in terms of cosmic rays, and it does matter for our transport equation that we go to sufficiently high redshifts. Okay, so this whole business of cosmogenic neutrinos is the subject of very intense theoretical and experimental work nowadays. And the reason for the theoretical work is because we have lots of uncertainties in the parameters of the cosmic rays that translate into uncertainties in the predicted neutrino spectrum. So we saw how the parameters affect the final spectrum of the cosmic neutrinos of the Earth. There's a lot more that can affect it, so our predictions are quite all over the place in terms of size, and that means that it's difficult to target a specific flux and build a detector that can catch that flux. And the other part, the experimental development part, is because we know for sure that we need as big a detector as possible to catch a very, very small flux of neutrinos. And it turns out that that requires some new kinds of detection technology. Typical neutrino detectors rely on neutrinos creating light and the detectors having photomultipliers that catch that light. New detectors will probably no longer rely at those energies on light, but on radio detection of neutrinos and other quantities like that. So I'll say a few words about that next lecture. But for now, let me stop here. Thank you.